recording. All right, so this is Operations Research, Math 317, Lecture 3. So what I want to do today is review a little bit of eigenvalues, eigenvectors, some of the applications. This is not a course in linear algebra. This is a course that uses linear algebra at times, and I want to just use this as a way to review and familiarize ourselves with some of the things you should have seen in linear algebra. And if you haven't seen them, at least show you how you can use these things to do calculations efficiently. It would be a little extreme to say the following. If you were learning to calculate eigenvalues, how did you calculate them? What did you use to find eigenvalues?
Determinant.
So determinant of A minus lambda I equals 0. And if you have some matrix A, where when you act A on a vector V, you just rescale its length, you call lambda the eigenvalue, and you call V the eigenvector. We always assume that V is not 0 when we're doing this, because then any vector, then the 0 vector would be an eigenvector every single time, and any lambda would work as its eigenvalue. This is a wonderful theoretical tool to find eigenvalues. If this is the only way you are finding eigenvalues, it's a tad extreme to say your professor should be shocked, but it's defensible. I could see my lawyers making some kind of temporary sanity argument. This is disastrous for matrices that are, say, 10,000 by 10,000. Okay, this is going to be a polynomial in lambda. We can do quadratics. We can do cubics. We can do quartics. That's it. This could be a polynomial of degree 10,000. Now, we have ways to try to make this more tractable. We can do Gaussian elimination. We can do stuff like that to try to simplify this, to move this into upper triangular form, and then read off the eigenvalues. But in general, you're going to have a tremendous amount of concern about the accuracy of these measurements. As you're doing these manipulations, if these are real-world values, what are you going to say about all the decimals and all the precision you're going to have? There are other techniques to calculate eigenvalues. It would go too far afield to do that. I encourage you, if you're interested, to actually look and see, how does one industrially compute an eigenvalue or an approximation to an eigenvalue? For a lot of things, we don't necessarily need to know exactly what the eigenvalue eigenvector is, but just something that's a pretty good approximation. All right, so why do we care so much about eigenvalues and eigenvectors? Well, if A is real symmetric, there's a beautiful theorem. There exists an orthonormal basis of eigenvectors. So what that means is, given any vector v, I can write v as a sum of, say, ci vi. I goes from 1 to n. And a of vi is equal to lambda I vi. And vi dotted with vj is delta ij vi. Delta ij. So this is beautiful notation. It's 1 if I equals j, 0 if I does not equal to j. I'll just make sure it stays in focus. So this is called the Kronecker delta symbol. My freshman math book said he is famous for more than just this. Good notation is valuable. This is a way to just quickly encode that the only time the dot product is not 0 is when you have the same vector, and in that case, the dot product is 1. So they all have length 1. They're all mutually perpendicular. If A is real symmetric, it turns out all the eigenvectors are real vectors as well. All right. Why is this so useful? Well, if I wanted to compute A of V, that's going to just be A of the sum over I, ci vi. But now we use linearity. A matrix applied to a sum of vectors is the sum of the matrix applied to individual vectors, and I can pull out the c's, and this is just going to be the sum over I of ci a of vi. But what's a of vi? Lambda vi. So this is just the sum over I of ci lambda I vi. And now the way that this becomes tremendously useful for us is that we could do this multiple times. If I applied the matrix twice, if I had a squared, and I just go through the calculation, I would have a squared of vi. Well, the first a hitting vi gives us lambda I vi. So a squared of vi is just a of vi is a lambda I vi. I can pull out the lambda I have a act on this, and I'll get lambda I vi. And so when the dust settles, I would get lambda squared. And in an absolute shocker, what should I do next? Yeah, cube it, or I could even say, there's no reason to even do cubes. Let's just go all the way to a general letter. So what letter should I use? That's why I was deliberately not writing the indices of summation. So you want to be very careful never to overuse a symbol. I was in a math class where the professor was less than stellar, and we eventually realized that the f on the left-hand side of the equation was not the same as the f on the right-hand side of the equation, even though they were written the same way. There was left f and right f. And then there was f followed by another letter, but anyway. So we'll use a different letter. We'll use maybe m. And so if we take the mth power, we see now it's very easy to compute the mth power of the matrix on any vector. This is one of the tremendous applications of having a basis of eigenvectors. We can do these calculations easily. We talked a little bit last time about conic sections, and that if you have an ellipse, how you can orient the axes so that you have the axes aligned with the ellipse. And what you can really do in a case like that is you'll have your matrix, and it will now be acting on those two directions as the eigenvectors. So I don't want to go into too much detail about the theory of eigenvalues and eigenvectors. I just want to quickly review what they are and quickly review why they are so useful. They allow us to do certain calculations with incredible speed. Okay? How would you calculate a to the m? So how would we find a to the 100th? So one possibility is to try to diagonalize A. And can I erase this? So we need to just compute a high power of A. However, in some sense we don't. Because if we have a basis of eigenvectors, we don't need A to the m. So in some sense it was a trick question. That's the power of having the... So if we knew the eigenvectors, we wouldn't need to compute high powers of A. In fact, as long as you have a non-zero component in the direction of the eigenvector with largest eigenvalue, you don't even need the other ones in the limit as it gets very large. It's going to dominate. But if I wanted to calculate a to the m, one possibility, as was suggested, is I can write a as q lambda q transpose. And then there are two schools where you put the transpose on the left or the right. Does anybody remember or care? Okay, since nobody remembers or cares, I'll just leave it this way because I wrote it. Q is an orthogonal matrix. So Q transpose is Q transpose Q is the identity. And now if you look at A squared, it's going to be Q lambda Q transpose Q lambda Q transpose. Q transpose is the identity matrix, and you just get Q lambda squared Q transpose. And more generally, A to the m would just be Q lambda to the m Q transpose, and lambda is just your matrix of eigenvalues. Is lambda unique? Could I have two different diagonal matrices? Yeah, if the eigenvalues are different. So you might sometimes say, I want lambda 1 to be the largest in absolute value going all the way down to lambda n to be the smallest. Or you could be contrary and go the other way from smallest to largest, doesn't really matter. If you do something like that, then you could have a unique choice of lambda. Another thing we could do is we could actually use the fast multiplication that we talked about in the first lecture and write m as in its binary expansion. And then calculate these values much faster when we need to calculate lambda to the m. But the whole point is there's a one-time cost in calculating Q that gives you Q transpose, that gives you the eigenvectors. If you can do that, then all the subsequent computations are extremely fast. We just have to raise real numbers to a power. We no longer have to do painful matrix multiplication. So you really want to be thinking, how often do I need to do this calculation? What is it going to buy me from doing this calculation? There are going to be times in the semester where we'll do a little bit of coding. And depending on how you write the code, the program can run either significantly faster or significantly slower. I think there's an example in the book about looking for pairs of numbers that satisfy Pell's equation. You want, I think, x squared minus 2y squared equal 1. And depending on how you write the code, it could take a couple of 100 seconds, it could take a few seconds, or it could take like almost no time at all. And you want to be very careful about which calculations are you having the computer do. Anybody have a program in Pascal? For a while, there was a craze to teach people easier languages than C, and so you would learn like a baby version of C and then transfer to C. There really wasn't much savings. So I learned Pascal when I was little, and I wrote a computer program to do a little game, and I had different levels. And depending on what level you were, the game moved faster. The way I did the delay, I didn't actually have a clock. So I just had the computer do a for loop, and I just had it, for I equals 1 to whatever. And the slower the game was, the longer it. Well, 10, 12 years later, I then run this computer program on a new computer. And the slowest version of the game was just barely playable, because of how much faster the processes moved. And you really want to be thinking about how long do these calculations take. All right, so let's do an application of matrices. So I am a number theorist. One of the most important sequences to study is the Fibonacci numbers. Some of you have looked at them with me. I am actually one of 12 members of the Fibonacci Association, the international governing board of the Fibonaccis. So if you have any issues with the Fibonacci numbers, you can come to me. If any of you do research with me on the Fibonacci numbers, I am actually one of the co-organizers of the next international conference at the University of Sarajevo in 2020. So if you're interested in stuff like that, please let me know. All right. There are a lot of ways to define the Fibonacci numbers. For what we're doing today, I will define them as 0, 1, 1, 2, 3. So 0, 1, 1, 2, 3, 5, 8, 13, 21, Big Poppy, 55. So each number is the sum of the previous two. Fn plus 1 is Fn plus Fn minus 1. This is a recursion relation. It's depth 2. Each number depends on the previous two. Okay? Once I specify any two values, I know the entire sequence. Because the recurrence relation allows me to compute. I don't have to specify two consecutive values. It just makes the algebra a little bit easier. Once I've given you this, as well as f0 equals 0 and f1 equals 1, everything you want to know about the Fibonacci numbers is contained here. It's just a matter of extracting it. Would it be hard for you to calculate the next element on this sequence? No. What would it be? 89. And the next number? 144. And you can ask, 144 is a perfect square. I wonder how many perfect powers there are in Fib. And so very quickly you can get some very challenging problems. But if you want to just compute the numbers, it's not hard. What if I asked you to compute the first 20 Fibonacci numbers? First 100? What if I told you your entire grade for the semester depends on calculating by hand the first 1,000 Fibonacci numbers? And if you do it correctly, you get an A+. We'll pretend we're a different department on campus. Would you take that deal? Do you think if you absolutely had to, you could do 1,000 additions? Yes. I would absolutely take the deal if I was in your shoes. What if I moved it to 10,000? How quickly are these numbers growing? Right? You'd want to get some idea about that before you do it. And maybe, if it's 100, I'm not worried about 100. But maybe 1,000 is a little bit large. So I'm going to do it slightly wrong. It's something like this. Lie-Sherrill numbers. Have anybody heard about this? So give me a two-digit number. 46. All right. 46 is not a palindrome. Okay? So I'm going to flip the digits and add. 0, 0, wait. I have to carry the 1, so that becomes 1. There you go, 110. No, it's hard doing this addition on the board. All right, is 110 a palindrome? So I'm going to write it in opposite order and add. Aha, it is a palindrome. And if you check all the numbers up to 100, you will see that every number, if you keep iterating like this, eventually becomes a palindrome. And if you go a little bit further, it still becomes a palindrome. Now, my daughter was given this in math class. I like her math teacher yesterday. Yesterday, in the English style of writing things, is 9, 10, 19. So you can understand why the teacher might be presenting stuff about palindromes. My daughter has practiced saying this with a straight voice. She's going to ask her teacher today, I found this homework problem really interesting, but we only looked at 1 and 2-digit numbers. Could we look at a 3-digit number? My favorite 3-digit number is 196. And she has a couple of justifications as to why she likes 196. This is the first number where we do not know if you eventually hit a palindrome. They have iterated this to the level of over 1 billion digits. It is amazing how much computational power has been spent on looking at this. And there are good heuristic arguments why almost every number that's sufficiently large will not end in a palindrome. Essentially, when you have a carry that causes trouble, and the larger your number is, the more likely it is that there's going to be a carry somewhere. But you want to get a sense of what is the magnitude of the computation going to be. If I ask you to compute the first 1,000 Fibonacci numbers, is this a deal you should take? 100, yes. 1,000, I'm not sure. So you would want to get some quick estimates. How big are the Fibonacci numbers? And again, this is one of the themes of the class, is if you can't solve the problem, can you at least estimate the answer? Now, it turns out for the Fibonacci numbers, we have an exact closed-form solution. This is Binet's formula, and we will see how to prove this many ways. One of the ways will be with matrices. Let's let phi be 1 plus root 5 over 2. Then the nth Fibonacci number is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5 over 1 minus root 5 over 2 to the n. This is one of my favorite formulas in mathematics. What kind of numbers are the Fibonacci's? Integers. So imagine that you've been beat up by a number, there's a police lineup, they're showing you the suspects. Does this look like the integer that beat you up? You've got divisions, you've got square roots, but miraculously everything cancels. As a nice exercise, what can you replace the 5s and the 2s with and still always get an integer? Now when you look at this, 1 plus root 5 over 2 is greater than 1 in absolute value. This is less than 1 in absolute value. So when n becomes very, very large, it's essentially whatever integer is closest to this part. And this will give you a rough sense of how large the nth Fibonacci number is. It's essentially the golden mean to the nth divided by root 5. And so if you now plug in n equals 1,000, that will give you a sense of how big your number will be if you want to actually calculate the first 1,000 by hand. We can get some estimates. Do you agree that fn plus 1 is less than or equal to twice fn? So we now know that this implies that fn should basically be less than 2 to the n. Maybe this, I'm putting this in quotes, maybe there's some issues with the small values in the beginning. I've got the 1 over here. But eventually, long term, it should be growing slower than 2 to the n. With a little bit of work, fn plus 1 should be greater than or equal to twice fn minus 1. So every time I increase my n by 2, I'm increasing by a factor of 2. So I should be getting maybe fn is greater than or equal to the square root of 2 to the n. And this is giving you that the Fibonacci numbers seem to be growing geometrically. Somewhere between root 2 to the n and 2 to the n. Now, these two functions grow at very different rates. If you look at them on a log scale, then comparable. But you have some quick order of magnitude understanding of what's going on for the problem. And that's one of the big themes for the class is when you have a problem, even if you can't solve it, can you tell me something about the solution? I want to solve this using linear algebra. So there is a tremendous amount we could do on this. But what I want to do is I want to show you how we can use linear algebra to solve something like this. So we have the recurrence relation, fn plus 1 is fn plus fn minus 1. I'm going to let v, I don't remember what I did in the book. I'll let vn be the vector fn minus 1. So Vn plus 1 is Fn plus 1 Fn. Well, but that's the same as Fn plus Fn minus 1, Fn plus 0, Fn minus 1. This is the same as 1, 1, 1, 0, Fn minus 1. Fn plus Fn minus 1, Fn plus 0, Fn minus 1. So what we've just shown is Vn plus 1 is, let's call this matrix A of Vn, which is also the same as A squared Vn minus 1. And now I keep going all the way down until I get A to some power acting on V1. Anybody know how many powers it should be? I'm sorry? It is n. A to the first plus n is n plus 1. A to the second plus n minus 1 is also n plus 1. So the sum of the power of A in the index is always n plus 1. This is a quick way to check and make sure I've got the right index. So it should be A to the n. So if I can just find the eigenvalues and eigenvectors of A, I can find a formula for Fn plus 1. I have to diagonalize this matrix 1, 1, 1, 0. I have to find its eigenvalues. I have to find its eigenvectors. This is not a 10,000 by 10,000 matrix. Can we use the determinant of A minus lambda I here? Very profitably. So we haven't taught you entirely useless things in the past. If you can reduce something to a 2 by 2 matrix, that's wonderful. This is a quadratic equation. We can solve it. We can find everything. So I'm not going to do the rest of the calculation here. I believe it's in the book. If not, it's a really good exercise for you to just review the linear algebra you're supposed to have seen, so that you can actually do the calculation and find what are the eigenvalues of this matrix. What are the eigenvectors? Can anybody look at this and quickly tell me the eigenvalues and eigenvectors? Some matrices are easier than others. So the trace is the sum of the eigenvalues. So the sum of the eigenvalues is 1. The product of the eigenvalues is the determinant, which is negative 1. It turns out it's going to be 1 plus root 5 over 2 and 1 minus root 5 over 2. If you add them, you can see you clearly get 1, which is the trace. If you multiply them, you'll get 1 minus 5 over 4, which is negative 1. This is the method of divine inspiration. If you know the answer, write it down and show, oh, look, the answer works. The problem is the method of divine inspiration is sometimes fickle. You're not always going to be divinely inspired. I wrote down Binet's formula. Once I write this down for you, how could you prove that Binet's formula is correct?
Use your test.
So that would give you evidence for it. How would you prove it?
Plug in 0, plug in 1, and then plug in n minus 1 and n plus 1.
Yeah, basically, I mean, you test the two base cases, and then you would show that this satisfies the same recurrence relation. Because if you satisfy the correct initial conditions and the correct recurrence, then everything is uniquely determined. Or you can do it by induction. There's a lot of ways to do it once you have the formula. So if you're fortunate enough to have an idea of what the answer is, then you're in great shape. Okay, any questions about this? So again, I wanted to just briefly review some of the results from linear algebra and try to emphasize the more computational side of them. And here, this allows us a very fast, efficient way to compute powers of the Fibonacci numbers. I would not want to take this matrix to the 1000th power. I would much rather find the eigenvalues, eigenvectors, do that calculation once, and then I get everything from that without trouble. Okay. So by the end of the first week of classes, people's schedules should essentially have stabilized. So after that, we will be getting into the real topics of the course. I want to just use the first week to review a couple of things and then extend some of the things you've probably seen. How many people have never seen a binomial coefficient? All right, we will do binomial coefficients fairly quickly then. So binomial coefficients. So n factorial is the number of ways to arrange n objects when order matters. So if you have offices in a student government, president, vice president, secretary, treasurer, the different positions are different. The treasurer is different than the president, is different than the vice president. A foreign dignitary once asked a US vice president, "What does the vice president do in your country?" And he famously quipped, "You die, I fly. On behalf of the United States of America, we're here to express our condolences at your country's loss of so and so." Different people have different jobs, different responsibilities. If you have a student council, the council members or the House of Representatives, in a situation like that, everybody is essentially equal. And so in a situation like that, order does not matter. So here, order matters. This is n times n minus 1 times 2 times 1. We define 0 factorial to be 1. And the interpretation of this is, how many ways are there to do nothing? How many ways can I order no objects? Well, there should only be one way to order no objects. There's one way to do nothing. Anybody know what -1 factorial is? How many ways are there to order -1 people?
Let me impression it didn't exist.
So we like to generalize things.
Is it even infinity? Negative or positive?
Yes. So what is 4 choose 3? This is 4 factorial over 3 factorial, 1 factorial. Has everybody seen this? And so this is going to just be 4. What's 3 choose 4? Well, if we use the same formula, that should be 3 factorial over 4 factorial, -1 factorial. How many ways should there be to choose 4 objects from 3? 0. I mean, right now the Sox essentially need to win more games than our games remaining to catch the Yankees. Right? We need to do this, what? Maybe around 16 games left, give or take. They need to win maybe 25. That's not going to happen. This should be 0. Well, 3 factorial, what's that? 4 factorial, what's that? The only thing that's left free is the -1 factorial. And so the interpretation for -1 factorial is this should really be some type of infinity. And this is an extension of the factorial function. And this is one of the things we want to do, is we want to take things you've seen before and extend them. In fact, we want to extend this far more to just the negative integers. We want to extend it to all real values. And it turns out there's a lot of wonderful properties when you do this, because now you can use the tools of real analysis to analyze the factorial function. I will end with another one. If you've taken probability with me, you're not allowed to answer this. What is -1/2 factorial? How many ways are there to arrange -1/2 of a person? The answer, of course, is the square root of pi.
Is that a Riemann statement?
No, but that's not a bad guess. It's the standard normal. It's the Gaussian. So if you have the normal, how many of you have seen the normal in a stats class or a math class? The normalization factor is 1 over the square root of 2 pi. The square root of pi is coming from -1/2 factorial. What we actually have is what's called the gamma function. So gamma of s is the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. And again, you always want to ask yourself, why am I studying this? Why is this a good thing to look at? The other thing to ask is, why would I define it like this? How would you change the definition for gamma of s? Yes?
Pull out the x. Well, actually, no, that's differential.
I dropped the -1.
Yeah, you would drop the -1. Why do we have a -1 there? You know, shouldn't this be gamma of s minus 1? And there is another function where if you put in a -1 over here, s minus 1, we call that sometimes g of s, or g of s minus 1. Here's the reason you write it like this. If you write it like this is the integral from 0 to infinity, e to the minus x, x to the s, and then you have dx over x. If I rescale x by 8, dx over x is unchanged. And so this is an advanced analysis result. This is a nice measure that transforms well under rescaling. If you do a little bit of work, you see gamma of 1 equals 1. Gamma 2 equals 1. Yes?
Would you mind elaborating on the intuition of -1/2 factorial pi as the square root of pi?
No, it's a calculation you get from here. I can send some notes on it. If there's time at the end of class today, I'll talk a little bit about it. It's a special value of the gamma function, and if you do a change of variables, you get the Gaussian density coming out. So gamma of 1 is 1, gamma of 2 is 1. You could basically evaluate this by integrating by parts. Any thoughts on what gamma 3 would be? Could this be the Fibonacci's? 1, 1, 2. Maybe it is the Fibonacci's. But then we do another calculation and we get gamma of 4 is 6. And we realize, nope. And then if you're clever, you realize you can write these as 3 factorial, 2 factorial, 1 factorial, 0 factorial. And with a little bit of work, you will have that gamma of n plus 1 is n factorial. So this is a generalization of the factorial function. But because it is now defined for all real values, tools from analysis are now at our disposal. I'll quickly try to get gamma by half. Do we have time? Yeah, I think we have time. So gamma of 1/2 would be -1/2 factorial. This would be the integral from 0 to infinity of e to the minus x, x to the -1/2 dx. This is screaming to do a change of variables. Let's let x equal u squared, or u is equal to x to the 1/2. So du is 1/2 x to the -1/2 dx. X to the -1/2, that's not bad. So I would get the integral from 0 to infinity, e to the minus u squared, and then this whole thing here becomes a 2 du. Well, the 2, I can just double the integral by going from -infinity to infinity. This is just the integral from -infinity to infinity of e to the minus u squared du. And now you can see the Gaussian emerging. And this is where, when you know what the normalization factor is from this, it has to integrate to 1 if it's going to be a probability distribution. You can then use that to figure out the gamma of 1/2 is going to be the square root of pi. All right. So what I want to do now is I want to talk a little bit about how you would prove some lemmas about binomial coefficients. We saw a video in the first lecture where we looked at Pascal's triangle mod 2. We looked at even or odd. If it was odd, we put a dot. If it was even, we removed the dot. And we saw a fractal pattern emerging. And what's interesting is it is possible to talk about non-integral dimensions. Now, when you're calculating binomial coefficients, factorials can grow very rapidly. And so it could be a computational challenge to actually determine these. If you have certain identities, that can help you compute things faster. So the question is, how do you prove identities? A lot of combinatorics comes down to telling stories. You have something that you want to prove, you show it's equivalent to something else, and you tell a story as to how they're the same. So the first one I'll do by Dr. Seuss. N choose k is n choose n minus k. There are two ways to prove this. The first way is to just expand out what they are and do algebra. N factorial over k factorial, n minus k factorial, n factorial over n minus k factorial, n minus k factorial. And when you notice that n minus k is just k, the algebra isn't so bad. There is another way to give a proof of this. Anybody familiar with the works of Dr. Seuss? Anybody know which one in particular would be useful for this? Yes? It's the Sneetches. There are two types of Sneetches. Those with stars on their belly and those that do not have stars on their belly. And in a shocker, the moral of the story is it doesn't really matter if you have a star on your belly or not. Here's two ways to look at this. I have n people, and I want to choose k people. Or I have n people, and I want to choose n minus k people to exclude. Well, if you're choosing n minus k people to exclude, that's the same as choosing k people to include. So the two are the same. So that's the first lemma. The second lemma is Pascal's triangle. And this is what allows us to calculate things very quickly. N plus 1 choose k plus 1 is n choose k plus, n choose k plus 1. So this is the fundamental relation that allows us to calculate Pascal's triangle. 1, 1, 1, 1, 2, 1. Each number is the sum of the one above to the left and above to the right, and you just have ones all the way down. Using this, we can actually calculate Pascal's triangle fairly quickly. So there's a couple of ways to prove this. The first way to prove this is by just brute force algebra. I know what the binomial coefficients are, substitute, clear denominators, simplify, and when the dust settles, it's proven. There's another way to prove this, and it's story time. All right, somebody give me a great college. Yeah, it should not have been that long of a delay. Somebody give me a...
Amherst.
Yeah, we'll leave it as that. So I want to choose k plus 1 people from n plus 1 people. We have n from Williams, and we have one person from Amherst. And I want to choose k people. K plus 1 people. There's n plus 1 choose k plus 1. I can split this and say, maybe I choose the person from Amherst. There's one choose one way of choosing the person from Amherst. How many people from Williams will I now need to take to get up to k plus 1 people? K. Or we could be in the nicest situation where we don't have the person from Amherst. And now how many people do we need from Williams? K plus 1. So a lot of times when you're looking at theoretical math texts, ones are hidden. And if you put the ones in, it actually makes it a little bit easier to understand what's going on. Really, there's two ones in Pascal's triangle. One of them is 1 choose 1, one of them is 1 choose 0. And when you put it in like this, you can see the story of what's going on as to how you're choosing people. There's a lot of combinatorial identities you can prove this way. This is not a class in combinatorics, but I just wanted to give you a little bit of a sense of how you would do some calculations like this. And this allows us to calculate each row from Pascal's triangle from the previous. This is very similar to the Fibonacci's. If we know the previous level, we can get the next without too much trouble. If you only care about things as to whether or not they're even or odd, then there's other things you can do. And so the book elaborates on this, and the book goes through more situations and talks about how you would do these calculations very efficiently. I just wanted to give you a little bit of a sense of how the combinatorics is done. One of the hardest parts in pure mathematics is simplifying expressions. My physics mentor from my undergraduate days knew his trig identities up to sines and cosines of 10 theta. And this is before symbolic computer programs. And by knowing things that well, he could often look at expressions and see how they simplified. And seeing how they simplify, it often gave him a better understanding of what was going on. This is why, whenever possible, I try to emphasize how do you look at these things to get a sense of what's happening. But telling these stories can be quite challenging. All right. Any questions on the combinatorics? We're not going to need anything really more involved than n choose k. There's going to be some times later when we want to know how many ways can we choose k objects from n to just get some sense of the relative size. I guess the last thing that's worth mentioning is how large is n choose k? We have bounds for factorials. So let's do size of. Well, Stirling's formula is n factorial is approximately n to the n, e to the minus n, square root of 2 pi n, 1 plus error of size 1 over n. And then you have higher and higher powers of n going further and further down. So one possibility is if n and k are large, you could do something like this to estimate n factorial, k factorial, and n minus k factorial. The other thing we can do is we have the binomial theorem. You should have seen this when you were doing calculus. You know, x plus y to the n is the sum, k goes from 0 to n choose k, x to the k, y to the n minus k. And you would often in calculus see y equals h to calculate x plus h to the n minus x to the n divided by h. You really only need the first two terms in the expansion. But this is the binomial theorem. Beautiful, beautiful result. Now, if I specialize x and y to different values, I can get some interesting results. If I take x equals y equals 1, I get 1 plus 1 to the n is the sum, k goes from 0 to n of n choose k. What's 1 to the kth power? And 1 to the n minus k power. So the sum of the binomial coefficients is equal to 2 to the n. In particular, any binomial coefficient is less than or equal to 2 to the n. You could do a little bit more. You could say the largest binomial coefficient is the one in the middle. And you could actually use this to get a lower bound for the size of the middle binomial coefficient. As a nice exercise, try to isolate a lower bound for the binomial coefficient of the middle. Okay. But again, this is just returning to our idea of trying to get a rough understanding of orders of magnitude of objects. So the last thing for today is dimension. Can somebody give me something that's one-dimensional? Okay, I was wondering if you were going to say certain people. Okay, thank you. So what was the one-dimensional example? A line. Something that's two-dimensional. Plane, three-dimensional. Space, four-dimensional. It's a little harder. Yeah, it's a little harder to visualize. Do dimensions have to be integers? All these examples are integers. So Hausdorf has a really nice way of defining dimension. So if you dilate by a factor of c, you can look and see how many copies do you get. So for instance, imagine we have a unit square and we increase everything by a factor, let's do a factor of 3. Okay? How many squares do we have now? 9. We increased everything by a factor of 3, and the dimension is the number that makes this work. 9 is equal to 3 to the d. If we increase by a factor of 4, and forgive the poor drawing, we would have 16 is 4 to the d. What would d be? It would still be 2. This would be a nice two-dimensional object. If you take a line and you double the length of a line, you have 2 copies. D is going to be 1. If you triple it, you have 3 copies. D is going to be 1. This gives you a nice way to talk about dimensions of sets. If I took a cube and I doubled it, how many cubes would I have? So if I had a cube and I doubled the length, doubled the width, doubled the height, how many cubes do I have? 8. And so for the cube, I would have 8 copies is 2 to the d. What should d be for a cube? 3. And this gives you d equals 3. So this notion is at least consistent with the notion of dimension that you've seen before. For a lot of these objects, it's nice, it works. But, and this is the key theme of the class, it works in new settings. So we could look at the Pascal triangle that we did, and we could put the dots in, and it's essentially equivalent to the following process. You take an equilateral triangle, and you throw away the middle. Then you take each triangle that's left over, and you throw away the middles of those. And you keep iterating. And the question is, what would the dimension of this object be? This is not necessarily the simplest one. We want to think of, if we were to expand it. Well, if I were to expand by a factor of 2, then this side here expands out to this entire side over here. This side would expand to this entire side. This side would be pushed over to here. This one copy here would end up becoming a whole copy of the whole thing. So if I double this, how many copies do I get if I double each dimension? I get 3 copies. So 3 should equal 2 to the d. What does d equal? Log base 2 of 3. And what can you tell me about that number? So I want something crude about the number. Yes? It's strictly between 1 and 2. The log base 2 of 2 is 1. The log base 4 of 2 is 2. This is strictly between 1 and 2. That's telling us that this is a set that functions as if its dimension is greater than 1, but less than 2. And if you think about it, I've got the solid lines over here on the boundaries. I'm never going to lose those. My dimension shouldn't be less than 1. I would be shocked if the dimension was greater than 2, given that it lives in the plane. I'm not surprised that the dimension is a little bit less than 2 because of all the stuff that's being thrown away. And it does make sense to talk about dimension like this. Why is this important? Well, we saw when we did Strasson's algorithm that we went from having n cubed to n to the log of 7 base 2. That a lot of problems, there's a dimensionality that controls how things are going. You really want to get a sense of the complexity of the system. How are things growing? How are things moving? All right. So this basically gives us a lot of the language that we're going to need. The next class, we're going to talk about the Euclidean algorithm. So every now and then, Professor Adams has a debate with Professor Garrity on various subjects. I was actually trying not to say Professor Adams' name because he got the short straw. He had to defend another bit of mathematics against the Euclidean algorithm. I mean, he gave it a valiant attempt. I believe Professor Garrity destroyed him in the Euclidean algorithm over the, I think it was the trefoil knot. We will talk about the Euclidean algorithm next time. It is a remarkable algorithm. And the reason I want to spend so much time on this is a first course in operations research. Real analysis is not a prerequisite. To go through and explain the runtime of a lot of the algorithms we're going to look at would be too much of an analytic diversion. What I want to do is I want to look at some algorithms that are similar in spirit, but are much easier to analyze and can give us a sense of how do you do these calculations and how do you look at the differences between worst case scenario and average case scenario. Maybe if I want to get some trivial balance, say I'll assume the worst thing happens every single time. It's the most unfortunate life possible. And then you hope to God that you are not in such a situation and that you can prove that you can't be this consistently unlucky. And the Euclidean algorithm is great for that. So we will continue with that on next class.